Welcome back to the Tinker-Pie Factory, everybody. We've now gone through several videos in this series to lay the groundwork for our project. In this video, we're going to put it all together and you're going to learn how to control this Arduino robot with an Android phone. We learned how to get started with the Arduino in number 19. Then we learned how to connect the HC06 Bluetooth module in number 20. In 21, we learned how to create the simplest of App Inventor Android apps. In 22 and 23, we connected that app to our Bluetooth module. Number 24 was for those of you who are using a Kindle. We had a minor hurdle to get over there. Then in number 25, we added the L298 motor driver to the mix and learned to turn it using our app. Finally, in number 26, we learned how to put together our Tinker-Pie robot. Now keep in mind, these videos will apply to any Arduino robot you may have. Like all new projects we get here at the Tinker-Pie Factory, we're going to start with a list of requirements. This is what we want our robot to do. It should be modular, meaning we want to be able to add more components to it like sensors. It should be easily controllable. It should be fairly inexpensive. And it should be easy as possible to program and modify. So based on those criteria, I decided to use the Arduino Uno because though it's not the smallest, it's usually the easiest board in the Arduino family. Because I wanted it easy to control, I choose the Android app developed using App Inventor because tilting the phone, I think, is more natural than pushing buttons, and App Inventor is super simple. All of these parts are fairly inexpensive, and the rechargeable batteries will save money in the long run. Let's open up App Inventor to where we left off in number 25. We're going to remove the test buttons. We don't need those anymore. We're going to focus on one task at a time and test as we go. Forward, left and right, reverse left and right, stop, pivot left, and pivot right. By breaking things down, we make the project less daunting, so let's get started. As we tilt the Android forward, the y-axis increases and x remains 0. So y represents the speed of the robot and x represents how far left or right we want to go. The formula we're going to use to calculate the speed is this. Speed equals 255 times y divided by 255, where 255 is the max speed of the motors. So this means if we tilt the Android forward all the way, our speed will be 255 times 255 divided by 255, which is 255. So that's full speed. Our accelerometer will go higher than 255, but we're going to cap it off. We're going to start by focusing just on the forward direction. X is negative in the upper left quadrant. Do you remember that Cartesian plane? I know it sounds like an airplane going to a really warm place, but it's this. The more negative x is, the tighter the turn. So if you can picture what the wheels are doing in this quadrant, the right wheel is going to the speed of y, and the left wheel is going slower. How much slower is what we're going to determine using this formula. Differential equals speed minus speed times x divided by 255. I call it differential because we want to figure out the difference in speed between the wheels. The bigger the difference, the tighter the turn. So again, let's look at that extreme example where x is 0 because we want to go straight ahead. We determined that the speed is 255, so the differential would be 255 minus 255 times 1 divided by 255. We have to make all zeros a 1 because we can't divide by 0. This comes out to essentially 255. In other words, both motors full speed ahead. Let's try this again somewhere in the left quadrant. When y equals 150 and x equals minus 100, then the speed is 150 and the differential is 91.5. The reason I call them speed and differential is because the wheel you set to either value will depend on the direction you're going. The speed is always the faster wheel. Let's go ahead and program this. We're going to first remove the test buttons we used in the last step. We won't need these. Then we'll pull over an accelerometer from the sensors group. Go into Blocks View and let's move the blocks we won't be touching out of the way. We'll be using the clock and we're going to drag over the accelerometer's on change event. Next, I'll create two global variables to hold x and y values from the accelerometer. In the accelerometer's on change event, we'll set those values. One little caveat here is that the values coming from the accelerometer don't match up with the Cartesian plane as we learned during the microbit series. The plus and minus are swapped. Since 3D printers and mills also have the left as minus, right as plus, I'm going to multiply by -1 to switch them around. Next, I'm going to write these values to the labels we created in the last video. Let's test the app to see how we're doing so far. You're seeing the x-axis as I'm tilting my Kindle completely left and right. We need the range to be minus to plus 255 in a comfortable range. In other words, we don't want to have to twist our wrists around to go full speed. This is called user interface design, where you think about how your product will be used and design with that in mind. Let's go back into the app, and I'm going to set this -1 to -60. I had to play around with this number to get the range right, so we wouldn't have to spend the time here. This process often involves a lot of tweaking and testing. We'll switch back to the Android app, which should automatically update, and now we can see the numbers are more in range. So far, so good. Our first task is to program for the forward motion. In that case, y is positive and x is either negative or positive. Let's set an if statement capturing that situation. We'll create two global variables to indicate the left-right direction and forward-reverse direction. If x is less than 0, we're moving left. If it's greater than 0, we're moving right. If y is less than 0, we're moving reverse. And if it's greater, we're moving forward. And now that we know the direction, we're going to strip the negative off of the x and y axes so that doesn't interfere with our formulas. Next, we'll apply our formulas, and we're going to create two variables to hold these values, global speed and global differential. The speed formula is speed equals 255 times y divided by 255. And we'll format that so it doesn't have a bunch of decimal numbers. If the speed is over 255, then we'll want to set it to 255 because that's our max. We'll use the speed to calculate the differential, which is the speed minus speed times x divided by 255. Again, don't allow that to be more than 255 and format it as a 0 decimal number. Now we're going to add some images to the screen that will change as we change directions. This is for feedback and because it's pretty. Remember when you're designing your programs, if it doesn't work, no one will want to use it. But if it ain't pretty, no one will want to look at it. So make it work and make it pretty. I'm going to add a horizontal alignment here and make it take up the width of the screen. Then I'm going to add another inside for a set width of, we'll try 170. The images have to be square or they'll get stretched, so we can't take up the full width. Let's add 3 more horizontal alignments and set their height and width to 150. I'm going to just upload all the images we're going to use at once. Then I'll set their images to see how they look. Let's rename these so we can identify them in blocks view. Next, we'll want to display this on the screen. And you'll notice that except for the initial reading of the accelerometer, I put everything inside the clock block. This will give you control over how often this event will trigger. If everything were inside the accelerometer on change event, it would likely overwhelm the program. I say this now because this is especially true for writing on the screen. You definitely want to limit how often you're doing that. We'll need to first reset these every time we enter the clock event. I'll place an if block, and if forward reverse is forward, then check for left right. If it's left, then we'll set the forward left image. Else if it's right, then set the forward right image. So what about just plain forward? We'll want to set a range in the middle that's somewhere to the left and right of 0 on the x. We'll say 30. In that range, we'll set the left-right variable to neither. Then we'll set the else to display the forward image. Now that we have the images all set, we need to send these values to the robot. Since we need to do this in these different if blocks, I'm going to write a function. The function will send the 3 values to the Arduino, first direction, then the speed of the left and right motors. I'll separate them with commas and end this string with a /n, which is a new line. We'll need to always pass the values in that order, direction, left wheel, right wheel. Now that we've created our function, we're going to call it first from the left. When the robot is going left, the speed is the speed of the right wheel and the left is differential. When the robot is going right, the speed is the speed of the left wheel and the right is differential. When we're going straight ahead, then both wheels are going the same speed. I'm going to switch over to my Arduino sketch. I'm starting out here where we left off in Turbo Tinker 25. The first thing I'll do is add the initialization for the second motor. Since I'm passing the values for direction left and right from the Android, I'm going to set up variables to hold them. Here, we were reading the serial port as a stream, 1 character at a time. But now I'm going to use this function called readStringUntil, which will read up until it reaches the string I specify, which is the /n. If you recall, that represents a new line, or as we used to say, a carriage return. Now that we have the direction left and right in the string, we need to parse out these individual values. And I have a function here that you can copy and paste. Just like the function we wrote in App Inventor, we're going to use a function because we need to call it multiple times, and I don't want to have to duplicate that code. So here I'm calling the function 3 times and passing it in the position 0, 1, and 2 because the array starts at 0. I'm going to use the actual serial port, not the software serial, to display some debugging information. No matter whether we're going in forward or reverse, the left and right wheels will go in the speed of the value that was passed in. So we'll set that first. The speed is set using analog write because we're using something called pulse width modulation. I'll have a separate video for that, but for now, think of it as a way of making something digital act like it's analog. Now I'll add an if block, and if the direction is forward, then set them to high-low, reverse set them to low-high, and stop set them to low-low. I'm going to go back and document my code, which is always a good idea. We're getting the string from the serial port, we're parsing out the values into variables, doing some debugging, setting the speed, then we're setting the direction, turning them off. There's the start of our sketch. It may not be perfect, but you'll find that with programming, it's a lot of test and tweak and test some more. Let's test this out by connecting to my Kindle using AI Companion. Immediately, I'm getting a divide by zero error. Remember how I was saying that you can't do that? Well, evidently I did it. Let's go back here, and here it is. This should be 255. Let's try this again, and now we're doing better. So now that we know that the wheels are working, let's finish out the interface. I wish you could copy and paste here like you can in MakeCode, but I checked and you can't. So we're just going to have to build these out. We'll create another row for pivot left, stop and go, and pivot right. Then another row for reverse left, reverse, and reverse right. It looks like I missed the reverse right image before, so I'll upload that. As always, rename the objects you intend to program so you can identify them in blocks view. Below the images, I'm going to put two labels for the formulas so that I can see what's going on. I'm going to pull over these two labels and just set them to speed formula and differential formula. We'll replace these in the code. At the bottom of the clock event, I'll set the text to those labels to show the formula with the actual current values plugged in. Now let's talk about these images and where to set them. If we're moving forward left, then we want the forward left.png file in the upper left box to display and no others. This means we need to set the forward left image and the rest to blank except for go. Go will be go unless we're stopped. But putting them here means that we have to duplicate all these blocks for the other directions. If you're copying and pasting your code, it's a pretty sure sign you're doing something wrong. Let's drag these over into a procedure, a subroutine which doesn't return anything. We're going to pass in the current direction and initially set all the block images to blank. Then we'll use an if-then to evaluate the current direction, and depending on what it is, we'll set the appropriate image. We haven't dealt with go, so we'll just set that at the top for now. Now we're going to call this procedure in all these blocks and pass in the direction. One more thing before we test this on the floor. Let's build out the reverse direction by copying the whole forward block. So, when the robot is going reverse into the left, which wheel is the speed and which is the differential? The right is the speed and left is differential, same as the forward direction. We could probably combine these two blocks into one and use variables. Often you notice things like that after you code something. When you go back and redo it, it's called refactoring. We'll come back to this in a later tutorial and refactor. For now, we're going to get things working. We need to change our directions for the image procedure. Here's our first test drive on the floor. Not too shabby. What I'm noticing here is that the steering is too sensitive, and I think the arrows should be as big as possible. But first let's finish out the programming, then we'll do some tweaking. Let's do the stop function next. When the Android is relatively flat, we'll want to stop. To give us a little leeway, we're going to say if x and y is less than 30, we're going to be going neither left, right, forward, or reverse. Then we'll add an else to our direction block to pick up this situation. We'll send stop to our procedure as the direction to set the images. Then we'll set global x and y to 0. That will turn our motors off. We'll add an if-then to the set images procedure so each pass will either have that image set to stop or go. Let's move to our final task, pivot left and pivot right. We'll also put this in the else block, so if we're not going forward or reverse, then we're going to evaluate whether we're stopped. Then we're going to check the x. So if we're not tilted forward or back, and we are tilted more than, say, 100 left or right, this code will kick in. If we're set to pivot left, we'll call the set images passing that in, sending those values to the motors. Else we're pivot right, we'll again set images and pass those values to the motors. Let's check our set images procedure and make sure we're accommodating these new values. We are, but the images are the same for left and right. Let's fix these. You might think we're done, but we didn't program the Arduino for this scenario. Let's pop back over there and add two else blocks for pivot left and pivot right. We'll switch the high-low on one of these motors. 50-50 chance I pick the right one. Let's make these minor tweaks before we try this again. First, I want to make these images as big as possible. I'll enlarge them as well as their containers. I also want to adjust the formula so that it doesn't steer so crazy-like. If you think about what's happening when it turns too sharp, the difference between the speed of the wheels is too much. This means we need to adjust the differential to lessen the range. I'm going to use a spreadsheet to work this out. We'll put the formula up here. This column is for our differential, and this column will have the x value. We'll set the speed to 255 and x to 255 to start out. Plug that formula in, then we'll change the x value down this column and copy the formula. The problem is right here. When one wheel is 255, the other is 0. That's too sharp of a turn. We'll set a multiplier, say 0.4, and multiply x. Plug that in, the differential is closer. Let's try this in our code. We'll set a global variable, plug it into our formula, then put it in the debugging at the bottom. We've really accomplished a lot in this video. We built out our Android app using App Inventor and wrote a sketch on the Arduino to control the motors. We learned how to tweak our formula to change the responsiveness and created an intuitive user interface. We're going to do a lot more with this, like adding the Raspberry Pi, so I hope you'll subscribe and join me for more adventures in IoT.